and development. The chemical process industry spend more money on research and development than do most other industries. As a result, we now use many kinds of products unheard of a few years ago. Countless items in our daily lives are different from those our parents used. Because of this innovation, much of our clothing is now made of synthetic fibers instead of natural materials such as wool or cotton. The toys our children play with are often made of plastics that replace wood or metal, and many of us drink instant coffee rather than brewing the beverage from ground coffee beans. These kinds of products have come about through research and development. I research laboratories. These laboratories are usually staffed by chemists who do their experimentation in the usual laboratory glassware. For example, when two materials must be mixed together, the chemist may do it with a glass rod or by merely shaking the container. The mixture can be heated by placing the container over a small gas burner or cooled by setting it in cold water. But many of the things that seem so easy in the laboratory are much harder to do in the plant. Even making the same product in the same way but on a larger scale presents many problems. Let us look at a very simple process as the chemist does it and as it might be done in a chemical process plant. He or she, many chemists are women, takes a bottle of chemical from a shelf and pours the required quantity into a glass measure. The chemical is dumped into a flask and a second liquid. Chemical B is measured, dumped into a flask and second liquid. Chemical B is measured and added in the same way. Chemical C, a powder, is weighed on a small laboratory scale and added to the two liquids. The chemist mixes the chemical together by shaking the flask and heats the mixture over a small glass flame with constant shaking. Finally, the mixture is rapidly cooled by placing the flask into a container of crushed ice. The chemist may have made a total quantity of half liters or less of product. Now consider the same process carried out in a plant in batches of 1,000 gallons. Most chemical plants in English-speaking countries still use the old units such as pounds, feet, and gallons. Instead of glass flasks, the container will be 1,000 gallons metal tank. Chemical will not be in a bottle on a shelf. It will be in a storage tank. The proper amount of chemical will be added by pumping it from the storage tank through a flow meter into the processing tank. Flow meter usually show flow in gallons per minute, so 500 gallons might be added at 50 gallons per minute. For 10 minutes, chemical B will be pumped from its storage tank in the same way. The operator will probably pump both liquids into the processing tank at the same time unless there is a danger in mixing them this way. Adding chemical C, the powder, is not easy. If only a small amount is needed, it might be weighed into a container and dumped by hand into a mixture. If larger quantities are required, chemical C will probably be stored in a hopper. Over there, processing tank, the hopper will have some sort of measuring, usually weighing, device to ensure adding the proper amount. Mixing 1,000-gallon tank cannot be done with a glass rod, so the engineers will have provided a mechanical mixer, sometimes like a ship propeller driven by an electric motor. The tank will probably heated by steam supplied to a steam jacket. Surrounding the tank, the mixture in the tank is stirred throughout the heating period to make sure it is heated uniformly. To cool the mixture, the steam will be shut off and cold water pumped into the jacket. Water cannot be cooled below 22 Fahrenheit or 0 derajat Celsius without turning to ice, but cooler temperatures can be achieved by using a solution of salt water called brine. Finally, the mixture will have to be pumped into another tank for storage or the next stage of the process. What has just been described is an example of a batch process in which a given amount of chemical is processed in same way to yield a quantity of product. Batch processes are commonly used when relatively small quantities of materials and handle, and particularly common when the materials are expensive. For example, batch processes are very often employed in the manufacture of drugs, dyes, and foods. Another widely used way of handling material in the continuous process, in which materials are constantly fed into one end of the equipment and finished product comes continuously out of the other end. All petroleum refining, for example, is done by continuous process. In a refinery, crude petroleum is pumped into one end of the plant and a continuous stream of gasoline, kerosene, and fuel oil pours out of the other end. Let us look at the simple process when have been describing mixing quantities of chemicals A, B, and C, heating and cooling, and see how it might be done as continuous process. I'm sorry for something mistake and any trouble, so I will continue my reading about this text. The two liquid chemicals are pumped by a proportioning pump into a small mixing tank, where chemical C is continuously added by a solid feeding device. The mixed chemicals are continuously drawn off the bottom of the mixer and passed through a heat exchanger, where they are steam heated. They then pass into another heat exchanger where they are chilled by cold water or brine. The products flow out of the end of the cold heat exchanger. Because chemical plant equipment is so different from that used in the laboratory, one of the major jobs of R&D engineers is to decide what kind of equipment must be used to carry out of commercial chemicals process. They also determine the size of equipment needed, how big must the pumps be, how much powder must the mixer have, before designing the full-size plant. The R&D engineer usually constructs a pilot plant, actually a small model of the final plant containing small version of the equipment. Pilot plants are particularly useful when designing continuous process plants, which are so different from the research laboratory. It is usually impossible to run a continuous process in the standard laboratory glassware available to the chemist. A continuous process pilot plant will usually run 24 hours a day with 3 or 4 groups of operators and engineers, each group working for 8 hours. This is called shift work, and each other is called a shift. Most often, shifts work from 8 a.m. to 4 p.m., 4 p.m. to midnight, and midnight to 8 a.m. A fourth shift is needed if the plant is to run during weekends, although many pilots plants shut down at the time. Usually, there is a group leader in the charge of each shift. The group leader may be a chemical engineer, a chemist, or a specially trained operator. This arrangement makes pilot plant experimentation unattractive to many chemical engineers who prefer to work during the day and leave the evening and the night shift to specially trained operators. However, a pilot plant is often so completed that engineers are required on all shifts. Since the basic purpose of the pilot plant is to gather information, there are frequent changes of flow rates, pressure, and temperature. R&D engineers are always looking for that combination of conditions that will enable them to process the maximum amount of product at the minimum price. As information is gathered, It is passed along the company's management. This may be done by memoranda and telephone call, but in most companies on a month, the R&D engineers write all they have learned during the past month in a progress report. This becomes their main record of accomplishment. The purpose of R&D is to gather information. Science accompanies management judges R&D engineers by the reports they submit. A great deal of work goes into the report's preparation. When the research and development project is completed, information in the various progress report is consolidated into a final report that details everything learned during this research. This final report is invaluable to the process design engineers who will design the full-scale plan. There is one thing about R&D that many engineers find frustrating. A project is seldom finished. As with all research, there are always more ideas than time or manpower. Eventually, the work must end, even in the best possible design has not been reached. Otherwise, no process will ever get into full-scale production. The designs to end a project is usually made by the head of the research laboratory in consultation with the executive of the company. Thank you.